So now that you've had the chance to understand the concepts behind the executor service and some of the key methods and some of the ways you can implement the executor service interface, let's show an example of how to apply the executor service to the PrimeChecker app. As you may recall from our previous discussion when we were looking at this in the context of the executor interface, this app is embarrassingly parallel and it's compute bound, and it uses this particular variant of this app uses the executor service to check to see if n random numbers are prime. This example also demonstrates how to handle runtime configuration changes in Android gracefully. If you recall, I talked before on Android, if you have your Android phone in one mode, like portrait mode, and you flip it to be landscape mode, it changes the activity that's running. And so this particular code here will do that in a nice, graceful, and efficient way. We're also going to show how to handle thread exceptions as well. So a fixed size thread pool is tuned to the number of processor cores in the computing device. And we've talked about that before. Here's the call to executor's new fixed thread pool with runtime.getRuntime.available processors. So that'll have, if there's 4 cores, you'll get 4 threads. As with the other example app, we have a user interface thread that's different from the pool of threads that are running here doing the computations. And this is responsive to the user interface, and it's going to generate random numbers that are then processed by the thread pool. Keep in mind that the fixed thread pool by default out of the box uses an unbounded queue to avoid deadlocks. Here's how we create a thread that'll run in the background to wait for the result. So there's going to be 3 different types of threads here. One type of thread is the threads that are part of the thread pool over here. So these are the threads there. Another type of thread is the thread here. That's the user interface thread. That's what's responsive to user gestures and requests. And then there's a third type of thread, which is a thread that is started to wait for the completion of all the futures in the list of futures. And the reason we do this is we don't want to have any blocking occurring in the user interface thread. So this particular thread is just going to wait for results to be completed by the threads that are running in the pool. Here's the class we're going to implement that's going to perform the check to see whether or not a prime candidate is actually a prime number or not. And we call it prime callable. If you go back and look at the previous implementation, you'll see we had something called prime runnable. And prime runnable was a runnable, and lo and behold, prime callable is a callable. So callable is another interface. We've talked about it before. The main difference between a runnable, which is what we had before, and a callable is that a runnable does not return any value, whereas a callable does. Here's the constructor. You can see it just stashes away the prime candidate for computation in a thread in the thread pool. Here's the call method. The call method is what's invoked automatically by the executor service when it's time for this particular task, this prime callable task to run, and this gets called back by a thread in the thread of the pool threads, or the pool of threads, and it calls the isPrime method. And we'll take a look at isPrime because isPrime is a little cooler this time too. What comes back from this is something called a prime result. And it's actually a tuple, and I think in later versions of Java, I actually implement it as a Java record. Record is a very interesting type that was introduced relatively recently in Java. I think it was Java 15 maybe, where records really came into their own. And what that does is a record is just a plain old data structure. You can have fields in a record. You might say, how does that differ from a class? Well, a class in Java can certainly have fields, but classes also contain additional state information. And that's because classes in Java can be used as something called a monitor object. So they have things in them like an intrinsic lock, which is a mutex or a rantrant lock. It's a variant of rantrant lock that is used to protect access to critical sections in an object of that class. Likewise, it also has a pointer to a virtual table to be able to access the virtual method calls. So objects have more state than meets the eye at first glance, and therefore later versions of Java introduce something called a record, which has only the fields and no v-pointer, no intrinsic lock, no nothing else, just the pure state. So you'll see some examples of that later. The use of callable with its two-way ability, it is able to perform computation and return a result, eliminates the need for a dependency in prime callable on main activity. In contrast, if you go back and look at the earlier version of this app that worked for the executor interface, we had to pass in a reference to an activity. And that was more coupling than we want. You'll see why that's important in a minute. Okay. So as a consequence, we don't have any dependencies, which cleans up our code quite a bit. Here's the isPrimeChecker method. This returns 0 if the parameter n is prime, or the smallest factor if it's not prime. And the key thing here is every time through this loop, we check to see if we've been interrupted. And if we have been interrupted, we break out of the loop. So this is a way of being able to interrupt a long-running prime number computation, which could take a while. If it's a big N, it can take a long time. And if it's prime, it's going to take a long time to run. So that allows us to be able to make the program more responsive if indeed you want to cancel it for some reason. The other thing we're going to have here is a list of futures to prime results. What the heck is that? So if you recall when we talked about the interface for ExecutorService, we talked about how you could submit tasks, or you could submit a task or a group of tasks. And what you get back when you submit a task is something that's a future to the result. And that's because the computation is going to run independently of whatever it is that you're doing. And you would like, you as the caller might want some way to control the task that is running asynchronously in the background, or perhaps waiting to be run asynchronously in the background. So what we're going to do here is we're going to end up submitting a whole pile of prime candidate requests to our thread pool, and we're going to get back futures for each submission, and we're going to store those things into a list of futures. And then we're going to use that list of futures to get the results, to redeem the results. And you'll see how we do this using Java sequential streams. Yes, sir. Yeah. Yeah, good question. The question is, what is a future? So future is a proxy to the result of a computation that is occurring or may occur asynchronously. And if you recall, I gave an example last time, I think, when we talked about the difference between classic McDonald's and classic Wendy's hamburger cooking models. And remember with Wendy's, when you place your order, you don't wait synchronously for the result. They hand you a little piece of paper, a little table tent number or something like that. That's the future. So it's a proxy for whatever you ordered, and you can go and redeem it at some point, or you can go to try to redeem it and say, hey, has order number 42 been finished? Can I get my hamburger, please? So that's how you can think of a future. But good question. So here's how we initialize this stuff. We create a stream of random numbers going from S max value to S max value minus count. And the reason for doing this is we want to be able to have duplicates. We want to induce duplicates here. So if count is large, this will give us more chance for duplicates. You'll see why we want duplicates later. It won't become obvious at the moment, but it will become obvious later. And again, the goal is to have lots of duplicates. We then use a cool feature in Java Streams where we take the stream of random long numbers that are pretty honkin' big, because S max value is like 100 million or something like that, or whatever it is, it's big. And we then use map to obj. That takes a stream of primitives, in this case a stream of longs, and converts them into a stream of prime callables. And this is a really cool example of what's known as a constructor reference. So this is a method reference called a constructor reference. It's passed to map to obj. And what this does is it takes each of those long values and creates a prime callable object that encapsulates the number. And then what we do is we use the map method, which is another streams operation, and we say, please take that stream of prime callable objects, which encapsulate the random large longs, and submit them to the executor service. So we'll talk about what mRetained state is later, but ignore that for a second. There's a field in mRetained state called mExecutorService, and we're submitting each of these prime callables by using map. And that will, as the little callout says here, it submits a two-way task for execution and returns a future that represents pending task results. So a future comes back here. And the last thing we do is we use the terminal operation collect in order to be able to take each of those futures, because remember, submit returns a future, and it takes each of those futures, collects them into a list, and lo and behold, we have a list of futures to prime results. And that's the beauty and magic of Java sequential streams. Those of you who've taken my other course recognize that. If you haven't seen that course, it's fairly straightforward. The cool thing about this, there's many cool things about this. One is it's functional. Another thing, you can read it from top to bottom once you understand the syntax, and you don't have to think about looping. And another cool thing about this is it automatically initializes the return result, so you don't have to remember to do it, and you don't have to call add, which is what you would do if you made a list through the more traditional way in Java. So very cool, very clean. I love stuff like this. Once you get into the mindset of understanding functional programming, I think it's a lot easier to understand these kinds of computations. There's also this other class called future runnable. This is what runs in a background thread, and it gets the results of all futures as they complete. So you can see futures runnable, or future runnable implements the runnable interface. So it has a run method. It has a field that keeps track of all the futures that we created back over here through this call in the main UI thread. And it also has a reference back to the enclosing activity, so it can print things out. The constructor initializes the list of futures in the main activity. And then here's the run hook method. Of course, a hook method is something that gets called back. It's a virtual method. It gets called back by the thread that's running the runnable. And what we do here is for each future in our list of futures, so remember we have a list of futures here, M futures. For each future, we're going to do some really cool magic. This is very, very, very cool stuff. I'll break it down because it's not entirely clear at first glance what the heck is going on, but it's really cool. So what we want to do is we're going to have this thread, because this thread's running in a background thread, so it can afford to block. It's not blocking the UI thread. It's going to block waiting for the next computation to be done. If there is a computation that's already done, it'll grab it, or if it's this computation, this particular computation, it'll get it, and as you'll see, it'll print the results out. But if there's not a computation, if this computation is not finished yet, then we're going to block. And so it'll wait until that particular computation is done. And this is an example of what's called a synchronous future processing model. We are waiting synchronously in some order, the order in which the calls were invoked, that were submitted, to get the results of those calls. There's pros and cons with this approach, mostly cons, but bear with me for now. This is a super cool little wrapper function or method called rethrow supplier, and you can read more about this approach. There's a class here called exception utils, which I did not put here. I imported it so I could keep the code so it would fit on one page. But basically what this does, it's called exception laundering. And what it's doing is it's converting typed exceptions, because our methods that take type exceptions. So future get throws an error, it throws an exception. And therefore, we would normally have to put a try-catch block around this, and it would be ugly as all get out. So instead we use the rethrow supplier exception laundering adapter, the adapter pattern from the Gang of Four book, to convert a method that expects a checked exception into a method that will now get a runtime exception. Exceptions will still be thrown if something goes wrong, but they don't interfere syntactically with the beautiful functional code. And rethrow supplier wraps this up and returns a supplier, and we can call the get method to get the result of this whole thing. Once we get ourselves a prime result, once we've got that particular future completing, we then check to see whether or not it was prime. If it was prime, then it's going to have the value of 0. If it's not prime, it's going to be non-zero, so we can produce the results and print them. And when we're all finished, we tell the main activity, hey, we're done, so you can shut down. There's also a neat method. This is what you can control from the user interface called interrupt computation. So you can click a button in the app's user interface which will say, stop doing the checking of all the random numbers to see if they're prime. And when that call is made, this method is invoked. And this method, as you can see, is going to turn around. Oh, so here's how you do it. This is the user interface, by the way. So here it is. It's doing a bunch of computations. We got 100 numbers that could take a long time. If we get bored waiting for them to finish, you just click that little button, and that calls this method through the GUI. And we then say, hey, executor service, shut down now. Do not pass go. Do not collect $200. Shut yourself down right now. And since I wrote the code to check to see if termination had occurred, that will in fact shut those tasks down right away. And then we also turn around and we interrupt the background thread, which also checks for this kind of stuff. So that'll return. So the UI thread will be shut down. Whoops, I should probably put a little thing here on the UI thread. So that'll be shut down. Sorry, the background threads will be shut down. In the pool, the background thread we spawn to wait for the futures will be shut down. And then we wait for termination. The user interface thread is going to wait until all the tasks have completed execution, and then it'll shut down. And we're going to bound that wait time by 500 milliseconds, but it shouldn't take anywhere near that amount of time to shut down. Here's something that's really here for Android purposes, again, to deal with this whole rotating your phone, configuration change stuff. We put all the state that we care about into a class called retained state. So we put our executor service instance, our future runnable instance, and our thread. We put all that stuff here, all the concurrency related stuff. And as you can see here, we make ourselves a future runnable. We stash it into retained state. We make ourselves a thread using the future runnable. We put that in the state. We also, as you saw, add the executor service. That goes in the state and so on. And everything is running in the background. And then we use some Androidisms. There's something called on-retain non-configuration instance. And what this will do is it will ensure that as the phone is rotated and the activity is created and destroyed, or destroyed and created, I should say, that state is passed from one instance of an activity to another one in order for the computations to continue to run in the background, even though we're changing the orientation of the phone. It's really, really, really cool. So if you really want to see this in all its glory, please go ahead and take a look at the app. The app is available in my GitHub repository. The link available there is earlier in the slide deck. And I think you'll be very amazed at how cool and powerful this stuff is. Now, we will see, of course, in the next part of the lesson that there are deficiencies even with this cool approach that can only be cured by other features in the Java Executor framework.